Welcome back to the series of lectures on high-performance scientific computing. Today we will review the use of directive-based programming for GPGPUs. So one of the ways to program GPGPUs using directives is OpenACC or open accelerators. So it's essentially a parallel programming model which is used to simplify GPU and accelerator programming. The good bit about OpenACC is that you could take existing serial codes, and if you want to use a parallel GPU or even say parallel multi-core CPUs, you can achieve incremental parallelization of this existing code. And this code could be written in C, C++ or Fortran. OpenACC also supports a wider variety of GPUs and other accelerators like NVIDIA GPUs, AMD GPUs, and so on and so forth. So why do we use OpenACC? First of all, it gives us a higher level of abstraction for parallel computing. Essentially, we can take a serial code and with the use of few directives, try to achieve some moderate to good parallel speedup. It is also portable across different architectures, both CPUs and GPUs. That means if I have a single code and I have different types of hardwares and architectures where I need to run this code. For example, I have access to only CPU clusters or only NVIDIA GPUs or different AMD GPUs. I need not modify my code, or if any code modification really needs to be done, it is extremely minimal. So it is portable across different architectures. It also supports what is incremental optimization. I can look at smaller bits of code and slowly optimize these codes so that they run faster. And compared to CUDA or even OpenCL, the development effort that is required is much lower. I do not need to completely redesign my algorithms. I can take my existing code and with little effort, I can get moderate speedups. So what is essentially the OpenACC execution model? So you have the host accelerator model, you have the host CPU which runs the main program, and you have another device which executes the parallel regions. These essentially are GPUs, but also could be only CPUs if you're on only a multi-core CPU machine. You can have explicit data management control of transferring data between the CPUs and the GPUs or the hosts and devices. You essentially mark the compute regions using a Pragma ACC directive. And those marked regions will now run in parallel. How do I enable OpenACC? First of all, you need to use an OpenACC enabled compiler, something like MVCC or GCC or the Cray compiler. So your compiler should be able to recognize these OpenACC directives and write the appropriate bits of code depending on the hardware that is present. Typically, the ACC flag is -ACC. What are the different directives that can be used in OpenACC? It's similar to OpenMP in some sense, but then the bigger advantage of OpenACC is the fact that it can offload things to GPUs. For example, you have hashpragma ACC parallel, which defines a parallel region. You also have hashpragma ACC kernels, which optimizes loops for parallel execution. ACC loop specifies parallel loops. The ACC data directive manages the data movement between the host and the device. And the ACC update does explicit data synchronization. A simple example for OpenACC is given here, where you have a loop which goes from 0 to n-1 and essentially is doing AI is equal to BI plus CI over these large arrays. Now, this is an embarrassingly parallel problem which can be easily offloaded to some sort of device, and in this case, a GPU. So you can have parallel execution across multiple threads where each thread is doing the individual BI plus CI and storing an AI for each specific index and thus accelerating the entire loop. We can control this parallelism. Remember, when we did CUDA programming, we were able to control the dynamic nature of the size of these workers based on the symmetric multiprocessor size. How many threads, how many blocks, how many grids. We can do explicit loops scheduling using hash pragma controls, like looking at gangs, workers, and vectors. So the gang is a high-level task parallelism which looks at blocks, similar to blocks in CUDA. The worker is the intermediate parallelism which is similar to the warps in CUDA. And vector is the finest grain of parallelism, which is essentially the individual thread in CUDA. So if you have this analogy right, you should be able to do a good control on this parallelism. Explicit data management. So typically we can do manual or automatic data transfers. So if you look at the directive ACC data, copy A, B, and C, essentially it tells that you need to copy the variables A, B, and C from the host to device. ACC update gives a directionality to where you want to update a certain variable. For example, update device is going to update the variable A on the device. You can do copy ins, which is basically a one-directional copy. Copy in A will copy the variable A from the host to device. Copy out B will copy the variable B from the device to host. Just create will only allocate on device, but it's not initialized to any value. And present D assumes that the data already exists on the device from some previous function. So, as in with CUDA programming, you have to minimize your data transfers. You have to optimize your data transfer because that's typically the bottleneck for any speed up. Data transfers between the host and device memory is often the slowest bit of performance. So you have to minimize copy operations to improve your performance. If you use present, it can be used to avoid redundant transfers. For example, if the data is already present, there's no need to copy it back to the host and then bring it back to the device. You can just say present and move ahead with your code. You can apply the hash pragma ACC cache for frequently accessed data. So this is how you typically use the data directive. You can also do reduction operations, especially when you want to reduce operations across parallel threads. For example, here we are doing a sum reduction across several threads. Reduction operations are supported in additions, in products, minimas, maximas, and logical ands and logical ors. And it can be done over loops. We looked at simple case studies of matrix multiplication where we were able to do loop collapses. Remember, again, these ACC parallel loops are the most effective when you're doing it on the outermost loops. If you go to the inner nested loops, your performance degradation will take place. So in this case, we are collapsing the two outermost loops and each thread is now doing the inner loop. So we use collapse 2 to sort of indicate the level of parallelization we want in these nested loops. Similarly, OpenACC is very good at doing image processing, which is sort of a very embarrassingly parallel problem. So you can do hash pragma ACC kernels to parallelize different pixel operations. Stencil-based CFT, we have looked at the Laplace's equation looking at successive over relaxation. We could easily do that using OpenACC directives. We can solve things like Navier-Stokes equations using OpenACC. So, for example, parallelizing pressure and velocity calculations across grid points can be done quite easily. We had also looked at doing Monte Carlo simulations. We had looked at very simple examples of doing the integration of any function numerically using Monte Carlo methods. You can also do very large financial calculations like financial risk analysis using OpenACC, and this really speeds up simulations. We also looked at debugging and profiling ACC programs. Profiling is very important because we want to identify regions of the code which are spending most of the time, and we want to parallelize those. We do not want to put the effort in parallelizing simpler bits of program where the time spent is low. This takes us back to our Amdahl's law, where parallel efficiency and parallel speedup is available only if we parallelize the largest sections of the code. We can use debugging techniques by using flags like nvacc notify to print the accelerator messages to see what is exactly happening and what sort of device code has been actually generated. We can also look with the minfo flag to look at optimizations, to see what optimizations are being done automatically by the compiler. So to look at the brief comparison between OpenACC, OpenMP and CUDA, both OpenACC, OpenMP and CUDA are all parallel models. OpenACC and OpenMP both are directive based, whereas CUDA is explicitly programmed. OpenACC is more portable because it supports larger number of devices, can go between CPUs and GPUs as well. OpenMP offloading has comparatively less support. The lowest level of support obviously is with CUDA, which works only with a certain brand of devices. Both OpenACC and OpenMP are relatively easy to use, whereas CUDA is far more complicated because you have to write a lot of low-level code, which inherently means that you have to put in a lot more development effort, and also the possibility of mistakes increase. But when you look at performance, OpenACC can give you moderate to good performance, whereas CUDA will give you extremely high performance because you're writing low-level codes. So to summarize, OpenACC simplifies GPU programming a lot. It allows for incremental acceleration of CPU-based applications. You can take a serial code and start putting in OpenACC directives to accelerate it both on multi-core CPUs and on GPUs. You have simple directives for parallel regions, loop control, and data movement. It's very useful for scientific computing, simulations, and HPC applications. Thank you.